only talked about enough with the quadratics that you guys could do the transformations in 1-7. So you could take a basic quadratic and basically shift him right, left, up, down. What are some other transformations? Stretch or shrink horizontally or vertical, or reflect, right? That's all that we talked about. That's the depth that we went in. We basically just said, here's a quadratic. Guess what? You'll have to transform him next section. This section says, no, here's a quadratic. Okay. So this section, we're going in depth on the quadratic itself. What was the title for chapter 2? Okay. In chapter 1, did we talk about things like zeros of functions? Yeah. We set functions equal to 0. We did some factoring of quadratics. But did we have to factor any cubics? Not really. Any quartics? What's a quartic? X to the 4th, like a quarter, right? Quartic, 4 quarters in a dollar. Quartic, X to the 4th. We didn't have to deal with higher ordered polynomials. Oh, no. This chapter, we're not just sticking with the basics, we're going in depth. And we're going in depth on 2 guys. We're going in depth on polynomials, which we're going to talk about for just a quick second, for a hot minute before we get into quadratics. But then we're also going to go in depth in future sections on rational functions. Do you guys know what rational functions are? Rational, ratio. What are ratios? What are ratios? Fractions. So if you have like an f over g, like a 1 over an x minus 1, like a 2x squared over a... Stuff's going to come up in this chapter like horizontal and vertical asymptotes. Stuff's going to come up in this chapter like discontinuities and holes. That's how all to do with rational functions. Oblique, slanty asymptotes. With polynomials, stuff's going to come up with all the higher order degrees and factoring, things like synthetic division, things like long division, things like end behavior, what's going on in general, trying to think about the graphs of these. Because it's going to get harder than just the transformations of last chapter, and we're going to have to think of things like completing the square. Vertex, well, let's just get into it. Let's just start with quadratics. Okay? Before we start with quadratics, a quadratic is the first introduction into polynomials. Lines are kind of their own dealio. Lines, they have a constant. They're not curved at all. They're either going up or they're going down, unless it's like horizontal and vertical. Lines, yeah, they're special, but they're not really polynomials. Yeah, you could call it a polynomial. It has multiple terms. But lines are kind of their own special deal. So are constant functions, like y equals c. So if you just had f of x equals this little guy, if all of this was gone, everything was 0, 0, 0, 0, 0, all you had was an a sub naught or an a sub 0, that would be a constant function, like y equals c, y equals a number. That would be a constant function. Is he curved? No. If I went one more term, if I had a sub 1 x plus a sub naught, doesn't this kind of look like slope-intercept form right now? mx plus b? Well, why are they using all of these little a's? Why not use like nice letters like we talked about before? Well, if they used m and b there, what would they use for the coefficient of that guy? Or of that guy, or of this guy, or of this guy? Polynomials can go however high we want. What if that's the 20th power? How many terms do you have? How many terms could you have if this was a 20th power? Why 21? 20th, 19th, 18th, 17th, yeah, all the way down to which one doesn't have, or to one that doesn't have an x. So you would have 20 different possible powers and then one more. We don't want to use like 20 different letters of the alphabet to talk about all the different coefficients that are possible. So what they've done is they've said, you know what? These a guys, they're coefficients. And this a guy, a sub n, is going to be the coefficient of the nth degree x. So for x to the n minus 1, I'll just call him a sub n minus 1. These are just names. They're just little names talking about the coefficients in front, and they're just kind of matching up with the different powers of x. Long story short, a polynomial function is addition or subtraction, because a's can be positive or negative. Addition, basically, or subtraction of terms with x's to powers. That's it. But what kinds of powers? Non-negative integers. Can we talk through really quickly, why does n need to be non-negative and only integers? What would happen, just real quick, non-negative integer, why? What happens, some of you are already thinking, good. non-negative integers. What would happen if we had a negative power?
Fraction.
X to the negative 2 isn't a polynomial because that's a fraction, 1 over x squared. Guess what? This would be a rational function. That's different. Different category. So negative powers are out because this wouldn't be a polynomial anymore. You'd be dividing by the variables. And then what's true if you had a non-integer, aka, we'll just say non-integer for now. A non-integer could be like a fractional power. What if we had x to something like the 3/2? What's wrong with him? There's a root all of a sudden. What kind of root? It's x cubed. Careful. X is cubed to the square root. So we don't write the 2 because it's understood, right? But these ones, that's called a radical function and that's called a rational function. Neither of those are polynomials. So we're allowed to have powers, but the powers have to be non-negative and integers. And we can say n is, it might help some of you guys, the nth degree. Have you ever heard that, even in like political commentary and stuff, like a pastor saying a sermon? Something about to the nth degree. That's not establishing the degree. It's basically indicating usually like high numbers of n. Like I don't know exactly what it is, but to the nth degree, like to this level of importance. The nth degree. We could also say something to the effect of, well, we haven't even talked about degree yet. We'll just say it's the power of x. And that determines what kind of polynomial it is. But you guys probably know, with polynomials, usually polynomials like you call a monomial that has 1 term, a binomial has 2 terms, a trinomial has 3 terms, and what do we call all the ones after that? Yeah, it's just a polynomial, right? But for these ones, polynomials, we also have to keep track of not just how many terms. It's not like Algebra 1 anymore. Now we're looking at the degrees that x is being raised to. We're going to talk about all sorts of different characteristics in future sections about higher degrees. But for right now, we're going to camp out on quadratics that have a degree of what? 2. All right, quadratics. Some of these are going to be repeats, but that's okay. We did a quick introduction in 1.6. We're going more in depth in 2.1. This homework isn't due until Friday, but just a warning, you are getting a worksheet tomorrow having to do with 2.1, so you're going to want to do as much of the book homework as possible tonight. Sound good? Okay. 2.1 homework is due on Friday, but that includes a worksheet and book homework, so the more you can do tonight, the better. Okay, definition, not like going way in depth in definition with words and whatnot, but we'll just say the one that you're used to seeing is an ax squared plus bx plus c. That's the most number of terms that a quadratic function can have. But a quadratic function doesn't have to have 3 terms. It could just have 1. It could have 2. It could have all 3. But what must it have to be a quadratic? You must have a degree of 2. So the one term that you can't lose and have it still be a quadratic is the x squared term. You can lose the linear component, you can lose the constant component, but you can't lose the quadratic or else it's no longer a quadratic. Standard form. This is where it's a bit of a struggle. This is the one that you're most used to, and so a lot of you guys would say that's the standard, but I already kind of introduced it in section 1.6. The standard form is going to be y minus k equals a times x minus h squared. You can write this another way. But really, it's the same thing. It's just moving the k to the other side. The nice thing is I totally saw from some Algebra 2 kids' homework that you guys have seen both of these before. And why is it so stinking useful if you can rearrange whatever form they give you a quadratic, probably this form? Why is it so useful if you rearrange to make it look like this? Who's h and who's k? The vertex. For a center, for a circle, it's the center. But for a quadratic, HK is the vertex. Remind me real quick. Is the vertex a max or a min? It depends on the orientation of the parabola. If Depends on the concavity, whether it's up or down. And Kyle, why did you say it depends on A then?
Because A is positive, is up, negative is down.
Yes. And why does that make sense mathematically? Isn't A multiplication on the outside? And isn't multiplication on the outside the only place where positive or negative you could get a reflection? Does that make sense? And so the vertex, real quick, is going to be a max when A is greater than 0. It's a little bit weird because it's a max when A is not greater than 0. This is not the normal way for a parabola, right? This is a reflected parabola. Happen to reflect it down. A would need to be negative, which would be less than 0. There we go. A would need to be negative, which would be less than 0. Then you would get your vertical flip, and then you would have the vertex being a maximum. So what's going to happen if A is greater than 0 and it's normally oriented? The vertex is going to be a min. Nice thing is, I mean, this is kind of easy to remember. What kind of people smile? Concave up like a cup? What kind of people smile? Happy people that are positive. Oh. What kind of people frown? Negative people. No, that's not, I know, it's a gross generalization. It's just a way of remembering. Pessimism, optimism. What's the one that period 6 calculus keeps on saying? If you're pessimistic, you're either correct or you're pleasantly surprised. Not sure that's a life motto to live by. We're not putting that on Share the Hope wall, but it's an interesting point. Just a little sad. Anyway, think about it. Product of linear pairs. If possible, actually not even if possible, in order to get a quadratic, if we take the whole like x squared come from x times x, you guys agree? So if x squared comes from x times x, doesn't it kind of make sense that there must be a way to take any quadratic and rewrite it as some sort of product of linear pairs? Now there's, I'm going to put a 1 in front just because factoring would be easier. Now here's the sad part. Can we just say something like that must be A or that must be B or that must be C or that no? So we're just going to use 2 new letters. How about D and F? Why not E? He has his own identity. But D and F. D could be a negative, so it could be x minus. F could be a negative, so it could be x minus some number. So D and F. There's this whole strategy of factoring. We don't need to talk about that right this second because we've reviewed it this year already. But the whole idea is there should be some sort of product of linear pairs that would make the quadratic. And why is that so nice? Because if we ever want to find the zeros, don't you remember we always have to factor first? And when we factor, we could set each one equal to 0. And when we set each one equal to 0, then we could finish off solving. But product of linear pairs, any quadratic should be able to be defined as a product of linear pairs. But here's the struggle. Are they always pretty linear pairs? Are they always nice numbers? No. No. And sometimes they're even imaginary. That's later. Okay. So, what? Why aren't we reviewing complete the square? I don't get it. What's the big deal? What on this page would force us right now, if we're getting more in depth on quadratics, to review complete the square? Where? Where is it required? Definition? No, not there. Keep thinking. What on this entire page needs complete the square? Actually, not this one, because this one says, I don't care who the two products are. They don't need to be squared. What does need to be squared? This one says, I don't care what the factors are, just factor it. Those are intercepts. This one says, no, no, no. To find the vertex, I need to have a perfect square. And sometimes it's not as nice and neat as you would like it to be. Now, let's put off to the side really quickly. There is a little cheater way of finding H. Not a little cheater in like a bad way, like you're losing your integrity way. It's actually really strategic and really nice as long as you're really good at mental math. If you could get a quadratic in ax squared plus bx plus c, you can always find h by plugging into negative b over 2a. Always. Always. So you actually wouldn't necessarily need to complete the square every time if you became a master at getting hk by doing negative b over 2a and then doing f of negative b over 2a. If you were able to find the x value of the vertex and then plug it into your quadratic to get the y value, if you were able to master that, well, you could actually know what h is and what k is without ever completing the square. So it's not as easy as maybe some of you just thought it sounded. So let's complete the square. First, real quick, in order to review completing the square, there's one thing you need to know. Quadratic formula. Now, quadratic formula, before we complete the square, don't worry, it's a precursor. We need to have this solid before we can even go into review and complete the square. So I'm going to show you where completing the square came from. If we needed to find the zeros, and you don't know who A is, you don't know who B is, you don't know who C is, right? We would use the quadratic formula. And the quadratic formula is what? X equals negative b plus or minus square root squared minus 4ac 2a. X equals negative b plus or minus square root b squared minus 4ac. Okay, nice. I have a kid who's a senior in college right now down at, where is he? UC Irvine? No. UCSD? Maybe. Engineering. He was in an upper div class. And at one point he had to remember the quadratic formula. Guess what he did and emailed me that day? Miss D, I was singing the quadratic formula. Thought of you in Algebra 1. I taught him Algebra 1 back in the day. It's like, Scott Uyakawa, good job, buddy, good job. Okay, saw him at church. He's doing well. It's awesome. But coming back. He's challenged, but loves Jesus, loving people on campus. It's good stuff. But coming back, where's the quadratic formula come from? You know the quadratic formula is really just like an America thing? I don't know if it's totally an America thing. But not all nations use it. Where does it come from? Magic. No. It comes from the following. What if we were to factor out an a and say, you know what, it's really hard to factor when there's an a? Because usually quadratic formula, aren't we using it for really complicated things, usually, that you can't just factor? So what if we take out the a and say, I don't like you because you make everything harder? I mean, he does. So if we pull him out, we would now have an x squared plus a b over a. Check it. I'm going to leave the c alone, though. What if we pulled out an a, saying, he messed things up, and he does. Pause. Am I correct? Would that be ax squared? Yeah. Would that be bx? Yeah. Why did I leave a space? Well, the problem is with quadratic formula, we usually can't factor this guy as is, so he's not good as is. So we say, you know what? I don't know exactly what to make you. But I do know that if I add something in one part to make you nice and factorable, I have to add it somewhere else as well. And actually, technically, to be honest, if you're adding one part, what should you be doing somewhere else to not make it off balance? If you add somewhere, you better, to make it balanced, subtract somewhere else, right? Now, what can we put here in order to actually be able to factor it? Well, you know what? I'm just going to say I'm going to make it a perfect square. That way I have a systematic approach to what I'm doing. Otherwise, without knowing b and a, I don't know exactly what to make my factors. And the only way to be able to use b and a to make is to do b squared over 2. I messed that. I don't like the way I wrote it. Hold on. b over 2a squared. Why? Well, if I take half of this guy and then square it, I know every single time I'm going to end up with that? How do you know that? Well, FOIL it, and you could double check. So if I was to FOIL it, what's x plus b over a times x plus b over a? Wouldn't that be x squared? And then when I go to multiply, I'd have one b over ax and another b over ax. So I would have 2b over ax. Now hold on, wait a minute. This doesn't match, does it? When you FOIL, you get double of this guy who's here. So if you get double of that guy who's here, what would I need in this in order to make it so the 2 doesn't mess me up when I go back? So it's not truly just b over a. It's half of that guy. And if it's half of that guy, then all of a sudden I'm like, oh, wait a minute, now it would work. Because I would have 2b over 2a. That gets me to b over a. And then I would have my b over 2a squared. When you FOIL, when you FOIL a perfect square, you get the square of the first, you get double of the outer and inner, and you get the square of the last. It's a shortcut that you could have memorized a long time ago. A lot of people don't think it's a very short shortcut. So they just say learn to FOIL and don't worry about it. But every time you square something, you square the first, you double the outer and the inner, and you square the last. This now matches up with that. And why is that so helpful? Well, hold on. We still need to make everything balanced. If I'm putting that in this blank over here, what do I have to offset it with out here? Yeah, I have to offset it with the exact same quantity. But wait a minute. What was on the outside of this guy? Oh, I have to make sure there's an A as well. Okay. Now everything's still balanced. What was the point of all this? Weren't we trying to find zeros? So if we're trying to do this process every time, if we're able to get to the squared, how can we get x alone without ever having had to factor or find its nice factors? Well, can't I add this guy to the other side? So I'd end up with a times x plus b over 2a, quantity squared, plus c. Well, actually, we can move the c and the other guy, and we end up with ab squared over 4a squared. That gets added, the c gets subtracted. Okay. Now what? Don't square root yet. Who do we have to deal with before the square root? Divide by a. So then we end up with x plus b all over 2a equals. If we were to actually distribute this over a, because dividing, that makes a complex fraction. Most of us are like, that's really, really gross. We could multiply by 1 over a. The 1 over a here actually cancels out, and we just get b squared all over 4a squared. And this one, we get c over a. Now what would we do? Yeah? And when we square root a squared, ooh, hold on, that's an absolute value. What do we have to remember? Plus or minus. Oh, that's gross. Wouldn't it be nice if we got like a common denominator? Because right now those are two separate fractions. Ugh. How do we get a common denominator? How about 4a over 4a? Oh, b squared minus 4ac. How do we get x alone? Negative b. Guess what you guys just did? Even though you might not have understood the entire process. You just found for yourself that the entire quadratic formula is really just completing the square simplified every single time. Completing the square says, I don't have what I want. I'm going to factor out any leading coefficients. I'm going to make this nice little perfect trinomial that ends up factoring to be the perfect square. I'm going to offset it somewhere else to be balanced and have this nice different form. But what I just showed you is really that's also what the quadratic formula does every single time. Yeah.
Will you ever make us to write these down?
Oh, I should, if I was a great teacher. in college, but no, I won't. Okay, complete the square. That was just a little tidbit of a nugget of cool information. You just derived, discovered, proved where the quadratic formula came from. But just because the quadratic formula is cool and there's a song and it's sometimes useful for zeros, complete the square is still really, 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 really necessary for vertex form, aka our standard form. So here's a review of complete the square if you need it. You always need to start with the leading coefficient of 1. And if you don't have a leading coefficient of 1, you're going to have to factor out an a from both the x squared and the x terms, but not the constant. Then you're going to form a perfect square by adding by 0 creatively, adding it inside the parenthesis and then offsetting it outside the parentheses by taking 1/2 of the x term, which ends up being 1/2 of the b over a term, which is what we saw on the page before, and squaring it. You're going to keep the equation balanced, either adding to both sides or adding and subtracting from the same side. Then you're going to factor and simplify into your form. And you can always check the vertex with our cool little cheater trick of, does h end up being negative b over 2a? Now here's the crazy thing. At the end of completing the square, you will have your h and your k. If you use the shortcut, you'll just have your h and you'll have to plug it into a nasty, possibly nasty quadratic and simplify a nasty fraction and a nasty quadratic to get your k, which for some of you would be harder and you would make more mistakes than just completing the square. Try to make it as big as possible. And as you guys write down the steps, I'm going to go complete the square with an easy one. I'm not finding zeros. Why didn't I factor anything out as you guys are writing? There's no a. A is just 1. Good. So leading coefficient's already 1. Forming a perfect square by adding 0 creatively. Well, I better take the middle coefficient. I better take the -7. Cut it in half and square it. That's what I'm adding in, which would be 49 over 4. And what I add on one side, add to the other, I'm just going to leave it here. Subtract from the same side. So if I subtract 49/4 somewhere else, I'm double checking it's nothing else. It's 1 times that. That's the ultimate quantity. Everything's balanced still. I haven't messed anything up. And why did I use -7/2? Because he is my term. Or is the number I use to factor into my perfect square. If you were to FOIL and make sure that you did it correctly, you would have x minus 7/2 and x minus 7/2, which would end up being x squared minus, there's going to be 2 of the outer inners, so there's going to be 2 7/2, and then our 49/4. Because of that 2, because of FOILing, there being an outer and an inner, that's why I have to divide this middle term by 2. That's the only way to get back to the original. But once I do have this, once I have factored into my perfect square, wait a minute, did anybody see that I made 12 48/4? Why did I do that? Oh, so much easier to combine. I end up with x minus 7/2 squared minus 1/4. Not only do I have my standard form, but I also know my HK of my vertex is 7/2 and 1/4. Careful. Plus k, it's not minus k unless it's on the other side. Plus k, it's a -1/4. Now some of you are like, psh, I would have just used the little formula. Okay. So if you did, could you have gotten -1/4? You would have had to do h is equal to, it might seem so much easier, negative b all over 2a. But after you get the 7/2, yeah, great, you got the first part of hk. But how would you have had to get k? Remember what I said? To get hk, you'd have to take your negative b over 2a and then go plug it in to your function. Plug it into what function? That one. Oh, that looks fun. For some of you, yes. For most of you, no. Because you would have to do 7/2 minus 7 times 7/2 plus 12 and simplify. 49/4 plus 12. Yes, maybe some of you could have gotten to negative 1/4 fairly quickly, but some of you freak out as soon as you see a fraction going in. This nice systematic approach will always get you to the end with your nice there's h, there's k, dun, 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 dun. So what happens if it gets harder? What would we do? Don't freak out, don't freak out. What would you do? Step number 1 said get a leading coefficient of, and the only way to do that is to, but only from the x terms. Then we would take the 6, and what do we do to the middle term? Cut him in half and square him, put him back up. So x squared plus, well, wait a minute, that's 36/4, right? So why over here am I going to go ahead and actually subtract 108/4? Why am I doing that? How on earth is that balanced? Those are two totally different numbers.
Or are they?
What's the struggle? What's 36/4? What should some of you guys have done before you even went up here? Hey, what's 6 over 2? Ah, what's 3 squared? That's a little bit easier way of writing it. But why would I not write 9? Why would I write 27? You guys can pack up and get ready to go. Why would I write 27? It's not really a 9. It's really a 27 that has to be offset. But do we have our vertex? The answer is dun 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 dun. Bye, cool kids. Work on 2.1. I'll see you tomorrow. Thank you for being in there an extra 30 seconds. I appreciate it. Complete the square. Easy for some, hard for most. But if we master it, it's a piece of cake. A piece of cheesecake. See you guys later.